Hello, I'm Pete Fryer. I'm the chair of the Heathrow branch of the Royal Aeronautical Society. Once again, tonight we'll be attempting to deliver a hybrid dual face-to-face lecture and a live online webinar. Tonight's event is the 7th lecture of the 2022-23 season of branch lectures. To you all, I wish you a very big welcome to the Heathrow branch of the Royal Aeronautical Society. It's great to see so many branch members, guests, friends, etc. here this evening. This evening, the Heathrow branch is delighted to welcome Dr. Guy Gratton as our guest speaker. Hello, Guy. Guy is no stranger to the branch and was a very good friend to us whilst working at the Brunel University in Uxbridge over the years. He has delivered several branch lectures to this branch, the most recent of which was Atmospheric Research Flying in the UK, presented as recently as April 2018. I think I was the chair for that one as well.
You probably were, yeah.
It was my first as chair. Guy is a professional pilot, engineer and researcher with a background spanning military and civil aviation, environmental science, flight testing and aerospace research. Currently, he's Associate Professor of Aviation and the Environment, working within the Centre for Aeronautics at Cranfield University. Previously, for 11 odd years, also at Cranfield, he was the head of the National Centre for Atmospheric Sciences Facility for Airborne Atmospheric Measurements, which included being responsible for their BA-146 research aircraft. And that was the subject of your last lecture, as I remember.
It got mentioned.
Yep. As I've already mentioned, before that, he was a lecturer at Brunel University, London, where he is still a visiting senior research fellow. Prior to this, Guy's been the Chief Technical Officer at the British Microlight Aircraft Association and Manager of Test Facilities, Trials Officer and Flight Test Engineer at MOD Boscombe Down. Guy studied for his bachelor's degree in aeronautics and astronautics from the University of Southampton. You were there. You started 2 years after I left. I looked you up yesterday.
All the grumpy lecturers was your fault.
Which one? Oh, Ken Bergen was always the most grumpy. Guy undertook a doctorate also at Southampton University in the development of new methods of airworthiness evaluation for aeroplanes. Guy has written many books on flying, airworthiness and engineering projects, as well as publishing 26 papers in academic journals on aspects of aeronautics. As a pilot, flight test engineer or mission specialist, Guy has flown over 2,100 hours in 115 aircraft types. In April 2022, he was the test pilot who made the first flight of the Sherwood E-Cub. Are you showing that tonight, or is it me that saw that?
No, that was just me playing.
Which is an all British, all electric microlight aeroplane. And he flew it from Little Snoring in Norfolk. In April 2010, he was the mission scientist on the first scientific flight into the ash cloud from the Icelandic volcano Eyjafjallajökull. Did I get that right? Goodness only knows. And if you remember, that one closed British airspace. The lecture tonight. Okay, the subject for tonight's branch lecture was identified last month, i.e. March, by our committee member Chris Pocock, who, if you're here tonight, booked you in. He'll be along up here in a second. So where are we? Last month, the Royal Society launched its policy briefing document, Net Zero Aviation Fuels, Resource Requirements and Environmental Impacts, which laid out the potential and requirements for aviation to change its fuel use in order to meet its future net zero climate impact commitment. As Guy was part of the leadership team for that report, he was Chris's obvious nomination to brief us, and upon checking, he was available and willing. Thank you, Guy. Thus, tonight in his lecture, Guy will describe the report's conclusions and the implications for the aviation industry. Right, bit of housekeeping. To all the audience today, if you have any questions for Guy, if you are watching the online webinar, your microphone has been muted. So I encourage you to pose questions through the Q&A window. which can be opened but from the question mark on your screen. You can also interact with us by clicking the thumbs up or like button next to each question that has been published. After the lecture, we will pose your questions to Guy on your behalf. If you require a CPD, Certificate of Attendance, for your own continuing professional development record, please use the Q&A button to inform us of your name, and our Secretary, William, will get those out to you after the event. Finally, I'd like to make you aware that today's session is being recorded, and there will be a recording available afterwards. I'm now going to pass you over to Guy, who will present his lecture, Net Zero Fuels for Aviation, the Royal Society Report and Beyond. Guy, I wish you a warm welcome.
Thank you very much
for coming. Over to you.
Well, good evening, and thank you for coming to listen to me. As has been said, my name is Guy Gratton. I'm a fellow of the Society, and I work between the aerospace engineering and environmental science areas at Cranfield University. So I'd just like to mention some of my personal history with the issue of net zero or greenhouse gas emission reduction. So I've been flying as a military flight test engineer, and more recently as a civilian pilot and occasionally scientist since 1990. And actually in 1992, though, I was working for the Ministry of Defence at headquarters in London. And I got called into my boss's office and said, I'm giving you a job to do to ensure we're complying with the Montreal Protocol, which sounded like it was something to do with spying on the Russians, but it turned out to be the removal of CFCs across the defence estate. Because work by British Antarctic Survey had shown what that was doing in terms of creating what we then knew as the hole in the ozone layer. So I've been around this for a long time, and since 2008, when I was first appointed head of the Facility for Airborne Atmospheric Measurements, I've been working in atmospheric science whilst remaining firmly both an aeronautical engineer and a pilot. But I've been working with a lot of the scientists who have been analysing the ongoing changes to the atmosphere and the consequent impact on our climate. I've also, since 2021, I've worked full time I've been working for Cranfield University since 2019. And since 2021, I've been specifically working on the development and testing of electric aircraft, including test flying the Sherwood E-Cub there, which we are still flying at the moment. About a year and a half ago, I got asked to go along to a meeting of the Royal Society, where they had decided they needed to do a government briefing document about net zero fuels for aviation. So I sat there in this meeting with a bunch of people talking about fuel pathways and pollutants and impact on radiative forcing and all things that are really important. And I heard them all out. And then I decided to be a bit awkward. And I stuck my hand up and said, what about the aeroplanes and the airports? Because nobody's mentioned them, and if we don't get those right, the rest of it doesn't really matter. And it turned out that I just volunteered to lead that chapter. So that's why I ended up working on this report, and that's how I ended up here. So firstly, let's just talk very briefly about the Earth's energy balance with space. And we've all heard a lot about it. I'm sure there's a few people in the audience who are skeptical about it. What I am going to say is it's not simple. This is the simple version for a scientist, showing the complex arrangement of energy in, energy out, energy bouncing, energy coming in from space, bouncing off cloud, energy being emitted from the Earth, being bounced back into the Earth off cloud. It's complicated. And what essentially is going on that we are calling either global warming or climate change is chemicals we have put into the atmosphere making very subtle changes to the chemical reactions, particularly around what's referred to as the UTLS, upper troposphere and lower stratosphere. That is shifting the energy balance and causing the troposphere, that's the lower level of atmosphere that we're all sat in at the moment, to warm. Now, this is not new science. The first publications suggesting CO2 emissions may cause warming were published in the late 19th century. But by the 1950s, this had become mainstream science, and the people who study climate were starting to think this is actually a significant feature we should all be thinking hard about. There was a brief period in the 70s when a minority of scientists said, actually, we think the world is cooling down. That science was fairly rapidly discredited, and we've continued to understand it as we have done since round about the 1880s, that man's emissions into the atmosphere are causing the planet to warm up. What is this doing to our planet? The troposphere, the lower level of the atmosphere, it's basically from here up to 36-ish thousand feet, high around the equator, lower around the poles, is warming up on average. And it's really important to appreciate this because it's changing the overall planet's behavior, and there will be places that are warming up by a lot more than the 1.5 to 2 Celsius we're currently worrying about. There are other places that will actually be getting cooler because of the changing patterns, but on average, it's warming up. By the way, the stratosphere, the next layer above, is actually cooling, and the tropopause, which is the layer between the troposphere and the stratosphere, is lifting. It's going upwards. It's also having an effect on winds. So winds around the planet, and I'm sure many of you have studied meteorology, it's basically driven by the temperature difference between the poles and the equator. And one of the things that is happening with climate change is that the poles are warming up more rapidly than the equator. Therefore, the temperature difference between the poles and the equator is reducing. And the effect of that is to reduce the strength of winds overall around the planet. The couple of graphs here, this is from a paper I led. Now, don't get hung up on the fact that this seems to say way worse than you're generally hearing. That's because I deliberately cherry-picked an airport that is particularly heavily affected to show the extreme. But this is Chios Airport in Greece, the red dot and the little map down there. And this is not a prediction. This is the data from the Chios Airport daily weather observations since for temperature just after World War II and for wind from the 1970s. And what we've got here is the average minimum daily temperature has gone up from round about 12 Celsius in the mid-70s up until round about 15 Celsius now. So we've seen about a 3 degrees increase in minimum temperature in 50 years. The wind, this is the mean headwind component on Chios's main runway. And what you can see is since the mid-70s, we were looking at a mean headwind component of around 16, 17 knots. And it's come down, and now it's down around 6 knots. That's the mean headwind component, because of course, if you reduce the wind strength, it also tends to change heading. And given that pretty much every runway in the world was built aligned with the historical mean winds, changing the wind heading will reduce the headwind component. So one impact of this is reduced revenue earning payloads off that runway, and there are other runways around the world where you can show the same. Clearly, this is not a universal pattern. There are places where the effects are insignificant. And as I said, I did cherry pick something to show the extreme. This is not indicative of the average around the world. So we know this is all caused by pollutants. We talk primarily about carbon dioxide, but as I said, my career started worrying about CFCs. There are also other gases like the NOx, the nitrous oxide compounds we worry about. So let's talk about the other side of this, because this is where net zero fuels come in. What's aviation's contribution? Well, you can see on this diagram, fossil fuel production and distribution are the biggies. Agriculture is actually the second biggest polluter in the world. And aviation is buried right down the bottom. Let's zero in on that. So this is the impact of 1 year's emissions from aviation on global climate change. Over a 10-year period, you can see we've got a breakdown here. It's about a quarter of our impact, maybe a third is from CO2. Then we've got a bit less of that from nitrous oxides. And actually, the biggest component is contrails. It's not CO2. When we go over 100 years, contrails are short-lived. And actually, the CO2 is everything. But it's really quite significant to point out that this is not the major contributor to climate change. And so, which raises the obvious question, why are we worrying about aviation's emissions? At the moment, our CO2 is around 2.5% of the world's CO2 emissions. That is the global aviation industry. We are really good at improving efficiency as an industry. Per passenger mile, our emissions are reducing by about 2% every year. That sounds quite good. However, particularly when we go into the contrail impact, our overall impact may be nearer 7%. So actually rather more than just 2.5%, albeit this is still less than 10% of the world's emissions. Here's another problem though. As an industry, we are continuing to grow. Yes, there was a glitch during COVID, but we're pretty much on an upward trajectory again. Our historical growth rate is about 5.3% a year. In recent decades, this is mostly air transport for the growing middle classes in countries like India, China, South American continent. So let's do a quick bit of maths. Subtract our 5.3% a year growth. Take that, subtract from it our 2% per year improvement in efficiency, and do a bit of maths. And what that says is our total emissions are increasing by about a factor of 2 every 21 years. So our industry's total emissions are doubling every 21 years. And we've got to bear in mind that is against a background of every other area of human activity reducing its emissions. So this is fundamentally why we in the aviation industry need to fix this, not because we're the major polluter now, but because if we don't fix this in the 2050s, 2070s, we are going to be the major polluter in the world. And that can't be allowed to happen. By the way, where's that 2% per year improvement come from? Quite a lot of it's from operational improvements, stuff that anybody who operates aircraft will be familiar with. We're flying less holds than we used to. We're doing better at delivering direct routings. Continuous descent approaches have reduced emissions. We're also operating aircraft closer to 100% occupancy. That's operational improvements. Technological improvements. Lower drag aircraft. I mean, just look at the front of a 747 versus a 380, and it's fairly clear that the 380 is a generation later and has cleaned up the drag around the shape of the nose and the windscreens and so on. We've electrified a lot of ground facilities instead of nasty, messy diesels on the ground. We've also got better at high temperature combustion within engines, which is producing less CO2. That may not actually be a win, because there's generally a trade-off that if you are producing less CO2 because you're burning hotter, you may be producing more nitrous oxide, which is a worse greenhouse gas. So that might not be a win unless you do what way too many people do and really crudely just measure the CO2 and don't think about anything else. And fleet replacements, because newer, better, more efficient aircraft are replacing legacy fleets all the time. And regulation changes, because the world's authorities, backed up by ICAO, have been enabling and enforcing all of these improvements. That's where our 2% has come from. So our emissions are increasing against a background of everybody else trying to reduce theirs. And unfortunately, we have a fundamental problem, is that a tank full of kerosene is just about the best way anybody knows of storing energy in a lightweight manner. So we are really reliant upon liquid hydrocarbon fuels. So how do we reduce emissions? First thing I would say is we should all be thinking about CO2 not being our major emission as an industry. Our major emission is contrails. Now, you may see some people say, well, the contrails are exactly 1.9 times more severe than our CO2. Anybody who's quoting it that accurately doesn't understand the science, because the science is still young. It's about double. It might be as low as 1.5. It might be as bad as 3. But contrails are definitely worse than CO2. We need to also remind ourselves that for the whole world, aviation is really, really important. Article from Forbes in 2020 reckoned that aviation industry supports more than 65 million jobs around the world. It is supporting a significant, albeit single figure percentage of the world's GDP. It is moving over a third by value of the world's goods and services. So shutting down aviation is not viable for the global economies. This is not the right answer. Flight shaming people into putting other people out of jobs, I do not see as a solution to the problem we have, but we still have a problem. And let's just remind ourselves, we've seen 2 major aviation shutdowns in our lifetimes. We've seen COVID and we've seen 9/11. How disastrous were they for families, for industries, for communities globally, just from the inability to travel by air? We don't want that, but we do need to fix our emissions problem. What's contrails all about? When we burn fuel, it doesn't matter to a certain extent what fuel and how we burn it, because piston engines will do the same. We create sooty particles. If we fly then that fuel burning aircraft in an area of air that is super saturated with respect to ice, which means it's over 100% humidity and it's below the freezing point, then those sooty particles act as cloud nuclei and ice crystals form around them. And what we get, and you can see here, which is just a photograph I took on a walk near my home, that we see the formation of what's essentially artificial cirrus cloud. That is what a contrail is. And it's fairly obvious. We all know, you go out in the winter, on a cloudy day, it's warmer than it is on a clear day. Why is that? Because the clouds reflect the heat back into the Earth that it is emitting as a black body infrared radiator. So that is what contrails do on net. There are portions in the day and portions in the planet where contrails will actually be cooling, where at the middle of the night, they're actually in the daytime, they are actually reflecting solar radiation back into space. But all of the current research says, on average, contrails are warming, contrails are a problem, and by about a factor 2 are worse than aviation CO2 emissions. Now, obvious thing that goes through most people's heads at this moment is, but they don't last very long. They last from minutes to maybe a couple of days for a really persistent one. That's absolutely true. The effect is so much greater than that of CO2, however, that they're still having that greater overall impact. But this does mean if we can work out how to stop contrailing tomorrow, by the end of the week, we've just shaved 5% off mankind's contributions to global warming, which in my book would be really worth doing. Can we do this tomorrow? No. Simply because right at the minute, our science is not good enough. We've got formula, something called the Appelman-Schmidt criterion, which predicts the creation of contrails. We've got weaker science that predicts their persistence. We've got other science that predicts its tendency to trap heat into the Earth and to reflect solar radiation back into space. In reality, that science is not yet good enough to allow us to do this, and we need to improve that science. We also need meteorological models, use the new science to predict contrailing and integrate that into air traffic management. That would be a fundamentally good thing regardless, because one of the problems most commercial pilots were well aware of any part of the world is most of the world does not have integrated meteorology and air traffic control. And actually, simply for safety, things like avoiding thunderstorms, integrating meteorology into air traffic management would be a fundamentally good thing. So we could be doing that now while we do the science, and then integrate the better science into the MET models, into the air traffic management, which would most definitely get my vote as the low-hanging fruit of reducing aviation's emissions. Anyhow, let me come back to the Royal Society. The Royal Society is the world's oldest, continuous, and arguably most prestigious scientific body. I missed the word continuous off the first draft of this slide, and somebody corrected me. Apparently, there is a slightly older society in Germany, but they ceased to function in the 1940s for 10 years, and therefore the Royal Society wins the continuous medal. And let's just remind ourselves who this society is. It's Isaac Newton. It's Barnes Wallis, it's Stephen Hawking, it's that enormous legacy of genius. And the society decided it was going to create this report, and it asked this fellow, Professor Graham Hutchings, he's the Regius Professor of Chemistry at Cardiff University, to lead it. You can see he's obviously not quite as prestigious as these guys because he only gets to stand in front of an oil painting. He isn't in one yet, but I'm sure that will come. So Graham put this together, and this report was published at the end of February. I'm embarrassed to say they sent me a box of hard copies to bring, and I left it in the office. However, that link there will take you to the report where you can download it. So for the 180 people at home, you have exactly the same position, and you can probably have read it by the end of my lecture. So the RS asked some exam questions. What are our net zero fuel options? What are the resources we need to deliver on that? What are the real, genuine environmental impacts of those fuels? And this is the question I force them to ask, and then they force me to answer. What do we need to do to the aircraft and the airports in order to deliver on this? That picture, by the way, this is a piece of lab equipment at Cranfield. This is actually us testing hydrogen combustion for future technology jet engines. Problem with hydrogen combustion, if anybody's interested, is it burns so hot that although it creates virtually no soot, although mostly its emissions are water, because it burns so hot, it causes the nitrogen and oxygen in the air to combine, and it creates nitrous oxide compounds which are worse than CO2, which is precisely why we've got this lab equipment at Cranfield, and we're trying to solve that problem for potential future hydrogen burning jet engines. So the first and most ideal solution is drop-in fuels, what a lot of people are calling SAF, Sustainable Aviation Fuel. Now, this report very deliberately never uses this term SAF. Why? Because it's too nebulous. There are too many different technologies and too many different feedstocks that you could group together with very different characteristics and call them all SAF. So we very deliberately avoided this term SAF, and we just called any individual fuel exactly what it was. Most of what's being talked about in this space, though, at the moment is biofuels. It is the use of agricultural products or waste products to chemically process and create a synthetic fuel that can be put into a jet aircraft tomorrow to allow it to fly. So the second problem we've got is have we got that computer is just how have we got enough feedstock to create the amount of biofuel we want? So unfortunately they're not in the same scale, but the top graph here is world sustainable aviation fuel production capacity in tons. And you can see here we're working in around 4 million tons a year of capacity. We come down here, we've got world jet fuel consumption in billions of US gallons. I did the maths for you. About 20 billion tons per year of jet fuel is needed. We are creating around 4.5 million tons per year of sustainable fuel. So roughly, we are currently able to furnish 0.02% of our jet fuel needs through biofuel capacity. This ain't brilliant. So we've got a fundamental feedstock problem here. So here's a question. What if we were just to grow all our own fuel? So we looked at several pathways here. Rapeseed, often known as canola. Miscanthus, better known as elephant grass, which is what's in the picture here, and poplar, which is a wood product. And we ran this experiment in a mathematical experiment. What if we try and grow all of our own jet fuel in the UK for the UK's departures? Well, what do we get? We've got these three sources that seem most promising. We run the numbers on what's the process, what amounts would we need, and we come up with, use rapeseed oil, we need 68% of the UK's agricultural land. Use elephant grass, and it's somewhere between 54 and 33%. If we go for wood, it's between 66 and 30%. So as an absolute minimum, we need 30% of the UK's agricultural land if we are to grow our own jet fuel. Now, around a decade ago, I went to a conference on this at ICAO's headquarters in Montreal, and a fellow from the United Nations turned up and said, guys, do everything you can to reduce emissions except jeopardize food security. That's the one thing you're not allowed to do. And I don't think that position has changed in anybody's minds whatsoever. So we have a fundamental problem here with feedstock. Now, you can go around the world, you can find countries who will have a better situation than us. You'll doubtless find other countries with a worse situation than us. But fundamentally, that is the elephant in the room of biofuels to make aviation sustainable. We just haven't got enough feedstock to make any meaningful quantity of jet fuel. And this is a consistent picture. What about the other things? If we could use 80% of the UK's used cooking oil, we can create 0.6% of the UK's jet fuel. Straw waste. We could produce, if we could have access to 50% of the UK's straw waste, we could produce 6% of our jet fuel. However, the farmers don't regard that as waste. They're all digging it back in to improve the soil. Forest waste. If we could take 50% of forest waste, we could produce 1.6%. But again, this is going back in, and it is sequestering carbon. You leave it to lie in the forest for, it rots in, the carbon is locked up in the soil, which is where we want it. Sawmill waste, 1.2%. Municipal waste, and she looks remarkably good. If we could have 30% of the UK's municipal waste, we could produce about 10% of our jet fuel. These numbers, any way you look at them, don't work. We can produce a percentage, and there's people like the Jet Zero Council working really hard to create a percentage of the UK's jet fuel out of nominally sustainable sources, but we are not going to get into a substantial reduction in our emissions. And as I said, all of this has other uses at the moment. There is no such thing as agricultural waste. If you're a farmer, it's all product, even if it's product that they then dig back in to improve the soil for the following year. And we are not the only people trying to reduce our carbon footprint. There are hundreds of other industries who also are sitting through presentations where people are saying, well, if we could have this and this and this, we could do that. And they're all after grabbing the same resources. Now, aviation may have an advantage because we're, relatively speaking, rich. So we can probably outspend a lot of other industries, but this doesn't really solve your overall problem. We might get into a few tens of percent, but we're not going to solve it. Which raises this question, is there actually any point in what are being termed sustainable fuels? Well, yes, there are, and no, there aren't. In the short term, any reduction in fossil fuel use has got to be beneficial because it is nonetheless reducing our emissions, and it is actually holding on to those resources that we might want for plastics manufacturing, for example, in the future. Anything that looks like a circular carbon cycle where we're growing stuff which has taken CO2 from the air, turning that into fuel, burning it in jet engines, and then that releases CO2, which we then pull back into the plants, etc., is better than taking fossil fuels and putting it out into the atmosphere. But the feedstock capacity limitations means this is not a total solution. And we have to keep remembering we are in competition with hundreds of other industries who all want that feedstock too. The staff standards, the best standards that I'm aware of, there may be new ones appearing, also offer around about 40% of the carbon footprint of current fossil fuels. Agriculture is not carbon neutral itself. So we can now, reducing our carbon footprint by 60% is well worth having, but it is not net zero. Just in passing, I think I am firmly off the Christmas list of Boom after they were announcing, look, our amazing use of sustainable fuels means we can be carbon neutral. And I stuck my hand up on Twitter and said, your fuel burn per passenger mile is 2.5 times what a conventional airliner is going to be. The sustainable fuel you're proposing to use has 40% of the carbon footprint of current fuels. Therefore, you break even on a British Airways Boeing 737. They didn't appreciate that, and they stopped sending me Christmas cards after that, I think. So medium to long term, yes, we still need to do biofuels. We still need to grab what we can now, but they are not our long-term solution. This is my message. This is not me saying don't do this, but this is me saying that is not your overall solution. We need new fuels, and at the moment, we've basically got 3 choices: hydrogen, ammonia, and efuels. And I'm going to go through all of these. Efuels is the only one that looks fairly similar to current kerosene and would allow you to drop it straight into a current jet aircraft. Start with hydrogen though. I like hydrogen. I think it has massive potential for solving our future problems. However, we don't know how to do all of that yet. So hydrogen, H2, comes in 3 colours. You may have heard this reference to grey, blue or green hydrogen. Grey hydrogen, which is about 95% of the world's production at the moment. This is take natural gas, superheat it with steam, and you pull off CO2, which you just dump into the atmosphere, and hydrogen, which you can then use in your hydrogen burning engine, fuel cell, whatever. Blue, which should be relatively easy to do. It's grey hydrogen, but instead of dumping the CO2 out into the atmosphere, you trap it and you pump it underground where the temperatures and pressures lock it down there so it doesn't come back. Blue hydrogen's clearly far better than grey hydrogen. The problem with blue hydrogen is it's still using fossil fuels. So we're still using that fixed existence resource. Green hydrogen is where we take renewable energy and fresh water, we electrolyze it, and we create hydrogen. That is 3, maybe 5% of the world's hydrogen production at the moment. But to be fair, there are a lot of very clever chemical engineers around the world working really hard to massively increase our production capacity globally for green hydrogen. So green hydrogen may be the answer to a lot of problems, and I am really interested in it. So we need this mass production, and let's just look at what we need to mass produce green hydrogen. I need a lot of renewable electricity. Roughly speaking, the UK would need between 2.4 and 3.8 times its current renewable energy capacity. So if you've heard any of these salesmen from Rolls-Royce saying what we need is Rolls-Royce to build lots of new nuclear power stations, it's entirely possible they are right, and that actually that is the thing we need to be doing. We also need a lot of fresh water. Now, lots of people have said to me, where are we going to get all the fresh water? So I went off and did some sums and actually pulled some water industry reports on leakage. And I determined that the UK uses about 12 million tonnes a year of jet fuel. Let's just assume less efficient and growth and so on and say we need about 20 million tonnes of hydrogen a year. That weight of hydrogen atoms is about what's contained in 10% of the UK water system's annual leakage. So actually, we've got the fresh water. That problem at least should be solved through the various water industry plans to reduce leakage. UK leaks 34% of its drinking water. That's about the same as France. It's a lot more than Germany, which is around 8%. I also discovered this wonderful euphemism for leakage in all these water industry reports. They call it non-revenue water. Can we build hydrogen aeroplanes? We've built hydrogen aeroplanes. The hydrogen islander there, okay, that hasn't flown. It's still in work. That's a company called Cranfield Aerospace Solutions. It's on the same site as my university, but we no longer own the company. They are working on that. Zero Avia, based at Kemble, they've flown this, which is a hydrogen fuel cell Dornier 228. They've previously flown a hydrogen fuel cell Piper PA46 Malibu. Airbus have got lots of plans. We can do it. We can't do it with current aircraft. So we need people like Zero Avia and Cranfield Aerospace Solutions and Airbus to develop us the new aeroplanes that will run on the green hydrogen that we're hoping that the chemical engineering industry is also going to work out how to produce. I think this can be done, but I would absolutely not trivialize how big a problem this is that has to be solved. But I certainly am totally behind everybody and anybody who is trying to solve these problems, because I think I don't think we should shut the door on any solution right now, but this is probably the one I would bet the most money on. Ammonia, what about ammonia? Ammonia NH3. So what we basically do is we use this as a way to carry hydrogen. So you run this through a catalyst, we crack it apart, we use the hydrogen in the same way we would in a pure hydrogen aircraft, and we dump the nitrogen over the side, adding nitrogen into an atmosphere that's already 78% nitrogen, not a big deal. Nobody's flown an ammonia aircraft yet. The safety issues are interesting. It's really hard to burn. It's pretty much explosion proof, but it's extremely poisonous. So you crash your ammonia aircraft, you shouldn't die in the fire, but you may die of asphyxiation and kill all the wildlife around the crash. Not necessarily the win you were looking for. There are ammonia research ships. This is BEng Energy, which was originally set up to run on liquid natural gas and is currently in conversion to run on ammonia fuel cell, specifically because the marine industry are interested in exactly the same questions that I am. So I am not discounting ammonia. I think it looks promising, but there is nowhere near enough research yet to either count it in or count it out. What are efuels? Efuels are scrub CO2 from the atmosphere, run it through chemical processes and create synthetic jet fuel. Now that we should be able to use in existing jet aircraft. It could be genuinely net zero by the simple device of scrub an excess of CO2 from the atmosphere, lock some of it underground, turn the rest of it into jet fuel, get your equations right. So that actually does look like a net zero fuel. And there are people working on this. Now, at the moment, it's about 10 times as expensive as fossil fuels. But it could, and the other problem is, we need a lot of energy. We need massively more sustainable energy than we've got at the moment. But it can be done. It has been done. The Air Force have done a single flight on synthetic e-fuel to prove they could in a simple two-seat aeroplane, but they did it and proved that point. You can see the numbers here. We're looking for 5 to 8 times the current renewable energy generation capacity that we've cut in order to create those e-fuels. And that's only for aviation. Don't forget there are other industries out there who also want more energy because they've got their own problems to solve. So my takeaways on all of this. Right now, aviation is not actually a major greenhouse gas emitter. So all the flight shamers, the Stop Flying Now brigade, they don't actually grasp the scale of the issues. They should be protesting again outside of our power stations and actually having very firm words with the farmers about their practices. But we have to solve the problem for the long term before we become the global baddie. Biofuels will not solve the problem in the long term, not on any solution I have seen. In the short term, they are an alleviator, and as such, we should be pursuing them. I'm fine with what the Jet Zero Council and the industry behind them are doing in the short term to create a percentage biofuel capability for the UK's airline industry, but it's not actually going to fix our long-term issues. And the industry is chasing the same feedstock with lots of other people who want to produce biodiesel for the roads, who want to produce biodiesel for ships, who want to use that for manufacturing new plastics. So we are not the only player after these resources. We are going to need new fuels in the short term, and in the long term, honestly, we need new aircraft. We're going to need we need things like hydrogen, maybe ammonia, quite possibly e-fuels, but we're going to need aeroplanes that can exploit the new fuels. Hey, we're a really clever industry. We can do this. We just can't do it by burying our head in the sand and saying recycling cooking oil is going to solve our problems.
Can I?
Yeah.
What are the changes in the aircraft design that will be appropriate for new technology?
Okay, so the question here is, what if we, let's say for the sake of argument, let's go for hydrogen, which is most mature. What are the changes in aircraft design we're going to need to build a hydrogen airliner? Well, we can start with the fuel tanks. So hydrogen, I don't personally think liquid hydrogen works because the amount of cooling you're going to need, you end up in diminishing returns. So we need compressed hydrogen. So we need an aircraft that can compress hydrogen and keep it compressed at 300 to 700 bar. And despite that, although weight-wise it's comparable with kerosene, volume-wise it's 3 to 4 times more in volume. So we're going to need aircraft that have got 3 or 4 times the fuel tank size. We're then going to need new fuel systems. We're then going to need new powertrains. We might burn the hydrogen in a jet engine. We might run it through fuel cells. Thank you for the phrase. We're also going to need to work out how we're going to get all this hydrogen to the airports and store it and get it on board the aircraft with all of the safety that goes around that. So in essence, we need new aeroplanes if we're going to go for new fuels. E-fuel is the only one that doesn't scream out, we need new aircraft.
Thank you.
Any data on the difference between the calorific values of hydrogen burning and the fuel
I
burning?
don't have them at my fingertip. Very easy to find online. Just honestly, just look it up on
Because
Wikipedia.
that is going to work out on the changes in the endurance with the given volume of fuel
Well,
that will be on board.
The weight is similar. The volume is greater. So basically, we need different shaped aeroplanes, but we shouldn't be necessarily looking at massively different aircraft performance.
Calorific values, because the kind of
Calorific value per volume will be much worse. Calorific value per weight will be similar. And that's why we need different shapes. And we all know we can make aircraft more efficient by simply flying them slower. So let's optimize these new aircraft to fly slower and tell the world terribly sorry, but the flight times your parents went on, that's no longer available to you. You're going to have to go on your trips more slowly than at present. And I'm just say we're going to need the new fuels, we're going to need the new aircraft. We need a lot more renewable electricity. There is no solution that is going to work without a massive expansion of renewable electric capacity. So all the people saying we need to improve the national grid, we need lots of new power stations, we need lots of offshore wind farms, they're all right. Whatever we do, that's all going to be needed. And the water, but I think we can probably fix that. I don't think business as usual is going to be an option. We just can't embrace that. Yeah.
What's the difference between hydrocarbons and biofuel? I thought it's roughly the same.
They are both hydrocarbons. It's the source that's the matter. So biofuel is still a hydrocarbon fuel. Now, there is some science saying that the relative simplicity of the chemical mix in a biofuel compared to a fossil fuel should generate less contrails. The science, I would say, is not yet definitive. There's just not enough research been done, but that's where the science seems to be saying. But basically, biofuel versus fossil fuel, they are broadly similar. Yes, there are some changes. Fuel seals, hose compounds, fuel gauging may need to change, but this is all manageable within existing aircraft.
But it would produce the same pollutants.
Broadly speaking, yes. So all we're doing is we're going into a closed carbon cycle rather than taking it out of the ground and shoving it into the atmosphere. And just to make a point, the UK does need to lead on this. There's always a bit of whataboutism in people's minds. What about America? What about China? Well, actually, it's only America and China that use more jet fuel than us. We are a huge consumer. So, okay, I would say this, I'm a researcher, but we need a lot of research. Contrail formation persistence and its behavior, we understand a lot, but we need to understand a lot more. Aircraft design, if we're going for new fuels, we're going to need new aircraft, and they ain't cheap. Our estimate at Cranfield is the cost of certifying a new hydrogen airliner is going to be around $30 billion, which is to say about 50% more than the cost of certifying the 787. So we're talking big numbers, but we're not talking unachievable big numbers. Airport designs, all of this is going to change the shape of the airports. If we change the fuels, if we change the aircraft, we are going to need to redesign our airports. And our people. I love this picture. I stole it off the website of RF Bryce Norton. It's a publicity photograph they did to show all of the people needed to get their A330 MRTT airborne. And clearly we've got aircrew, we've got firefighters, we've got chefs, we've got administrators, we've got a padre. But when you think about all of the changes in supply, in safety, in management, in operation, for my money, the only two people in that picture who will not need retraining with new aviation fuels are the padre and the chef. Every other professional in aviation is going to have their job changed by these new aviation fuels. But honestly, I think we need to embrace that. I don't think we should be fighting it. I think we need to embrace it. And actually, I seriously think this is the government's view, and they are more or less right, that if the UK grabs this and tries to take a lead, it could actually be really good for our economy. It could create a lot of jobs. It could be really, really interesting. Don't let other people take the lead and then take the high value jobs in, put bluntly, saving the world. I'd also make the very fundamental point, we can't do this on our own, not as an industry. The big player we need is the energy industry. Every possible solution needs a massive increase in the availability of renewable electricity. We also, if we are using biofuels, we need agricultural and waste industries to do their bit. Without doubt, we're going to need the chemical and petrochemical industries to do their bit, because whatever fuel we use, They are the people who are going to be supplying it for us. And by the by, we also need, for most solutions, the water industry. We're going to need a lot of fresh water, which basically means that their water industry needs to massively sort its act out and stop leaking such huge amounts of water into the wrong parts of the ecosystem. Because we need that fresh water, and so will other people. And that, pretty much on the hour, was my summary as an aviation professional of the Royal Society report and what it means to our industry. So it means a lot of hard work, it means a lot of change, but it does not mean the end of our industry. It does not mean a disaster, but I would say it does mean an end to complacency, that we are going to have a lot of things to do if we are going to prevent the rest of the world putting the screws on aviation in a way we don't want. So we are going to have to work, yes, with other industries, yes, with regulators, but this is our problem to own and to solve. But I genuinely believe we can do this. We just can't do it by business as usual. If anyone has any more questions, I'm here till we get thrown out. So.
Yeah, hi. When you talk about airport redesign, what have you got in mind?
So the question is, what do we need to do in terms of airport redesign? Well, take all of the gates that are around us here at Heathrow. They are basically designed around the assumption that aeroplanes are a long metal tube with a couple of relatively thin wings. If we are starting to go for things with much more bulky fuel tanks, then we may well be heading towards flying wing configurations. I know we've been reading that the next generation of airliners are going to be flying wings since the 1940s. It might finally happen. And if it does, none of the gate designs at Heathrow are going to take that aircraft. So there's one. We are going to have all of the supply for whatever our new fuel is to get it to the aeroplanes. And if we're going to do that, we need new distribution systems, we need new storage systems. There's going to be huge hole in the ground being dug to put the pipes and tanks. We can't run our new ultra efficient airliners and then service them with diesel ground vehicles, can we? So we're going to need to start, I mean, I know we're already doing this, but as much as possible to be electrified, built in, and so on. So, and then you're going to get into simple things like, well, if the type of fire they're going to fight is changing, we might have to redesign the fire station. So I think it's going to be pretty wholesale, but start by thinking about the new fuel and the new shape of the aeroplane and work outwards.
Sounds like even more disruptive here than having a third runway.
I think that is a very fair comment, yes.
It's interesting you focus so much on contrails. At a talk in Hamilton Place a couple of years ago, the then director Brian Burrows said that in his RAF days, so many years ago, avoiding contrails was the day's bread and butter. You know, you don't want to be spotted by the Russians. You know, you avoid contrails.
The last talk I gave to this branch was on Met research flying, and I actually described a research project in 1942 to try and eliminate contrails because of our high altitude bombers over Germany. Now, I never really got to the bottom of whether we solved the World War II contrail problem, but around 10 years ago, I found myself having a beer with a retired U-2 pilot from the US Air Force. So I thought, what an opportunity. So I said, right, how do you prevent contrailing when you were busy spying on the Russians at 60,000 feet? And he said, oh, it's really easy. We're a rear view mirror just above the canopy and I keep an eye on it. And when I start contrailing, I change altitude till it stops. Now that works fine if you're a spy plane over Russia at 60,000 feet. It does not work if you're in the NATRACs, because when aircraft for perfectly sound safety reasons have to maintain in bang on their altitude because there's another row of aircraft at 1,000 feet above them and another row of aircraft at 1,000 feet below, climbing and descending or going around because you've got another aircraft 5 miles on each wingtip, is not a viable way to prevent contrailing. So we're going to need, we can predict adequately well contrail formation. We need to do it better. We're really bad at predicting contrail persistence. If we can predict that and we can integrate it into air traffic management, then actually we can build it into the flight plans. And if we can, we may have to burn a little bit more fuel and generate a bit more CO2. But if we burn 2% more CO2, which is a realistic number, to eliminate all of our contrails and 2/3 of aviation's greenhouse gas emissions, in effect, that was a win.
But the trouble, surely, what the next stage is that actually airlines are incentivized to reduce and to minimize fuel burn. And so you need some sort of incentivization to actually.
So the point here is where the sheer cost of fuel incentivizes airlines to minimize fuel burn. How do we incentivize the removal of contrails? That is fundamentally a regulatory and economic question, but you're absolutely right. That problem needs solving if we are going to go into contrail prevention. So,
how do high bypass jet engines affect the formation of contrails? Is it the case that the higher the bypass ratio, the lower the emissions, the lower the formation of the
so the question is whether high bypass engines reduce contrail formation, and I'm afraid I'm going to duck the question because I simply don't know. The thing you are trying to do is predominantly reduce the production of soot. Now, I can think of a professor who could probably answer the question, and if you want to email me, I can pass it on. But honestly, that has slightly got beyond my knowledge base, so I'm going to duck the question. Sorry.
There might be a clue here. I remember years ago, we used to see a lot of contrails from aircraft that dissipated quite quickly, that simply didn't exist, relatively close behind the aircraft. I don't think I see that now. So whether that's got something to do with it.
Those still exist if you go looking for them, and we believe that the number of flights that are contrailing is below 10%, and it may be as low as 3 or 4%. So we may only have to reroute a small percentage of flights in order to prevent contrailing. And equally, persistent contrails are the problem. The ones that dissipate in a few minutes are not the problem. It's the ones that sit around for a day happily radiating or reflecting infrared back into the earth are your problem. It may also be that things like efuels, although very expensive, if we put that, because that's much cleaner, it generates a lot less soot. If we put that in the aircraft that we know are going to fly into the areas of supersaturated air, that may be another strategy for reducing contrails. But all of this, honestly, I get frustrated because I just don't see enough research and enough buy-in to understanding this issue and to cracking it, because it is solvable. And I just don't see enough political and financial will being thrown into solving the contrail problem at the moment. We've still got to solve CO2, without a doubt, but contrails should be low-hanging fruit that we should be throwing a lot of resource, in my opinion, in the short term into solving.
Guy, I think anecdotally, you could say if you see a 747 flyover, it has a far more persistent contrail than a 787.
I think that's highly likely because a 747 has the older, dirtier engines.
Yeah.
Yes.
That is very noticeable. I think that.
I think you're almost certainly right. I haven't looked for that myself. I'll go and look for that now.
No. Well,
yes.
I live just close to here. It's Contrail City, you know, so you just can't help but notice that.
Was somebody
There's much of a saving with futuristic hydrogen powered ramjet technology. Obviously the jets will be flying a lot closer to the drop, much greater altitude. Is there much of a net saving based on that over current propellant?
So the question is whether hydrogen ramjets operating in the vicinity of the tropopause may provide a significant benefit. That's difficult to answer. I think we are going to create less. I mean, we will probably largely eliminate contrails because hydrogen burning tends not to create much soot because there's no carbon in there to create soot particles from. However, you are starting to get into the question of what about the water you are now injecting round about the tropopause. And the science on that is still young, and this also emphasizes an important point. We need to research a lot into this to make sure we don't make some horrendous mistake by creating a worse problem in trying to solve the problem we've got at the moment. We don't want the aviation equivalent of Australian cane toads, basically. So
what research is being done to make this science, which is great that it's advancing, more accessible to the general public? Because that in turn might translate into commercial pressure to give the aviation sector the impetus for change. Because without that commercial pressure, it feels as though things are going to advance much more slowly.
So the question is really what's being done to tell the world about this science and what's needed. Well, it's to a certain extent, it's people like me turning up and talking at Heathrow. It's the Royal Society report, which is accessible to everybody. So I just wanted to get that slide back up for everybody, particularly the 180 people online, because that bottom one is the link to the report. And certainly I've gone with a group to go and explain this in Parliament to the Aviation Minister. Various of us have, if you go on BBC website, you can find me talking about this with a bunch of other experts on BBC Ideas. There's been articles in most of the major newspapers. We are trying quite hard to get these messages across, but sometimes it is quite difficult, particularly when there's more immediate things like a war in Ukraine and so on that are catching people's attention. But all I can say is we are trying our best to communicate this because we do really think this matters. So,
but sometimes it's quite difficult, particularly when you do things like rent and so on. All I can say is we are trying our best because we really think
so the question is whether there's research going on to reduce the cost of the alternative fuels. Yes, is the simple answer, because the people who are producing these, the researchers, the petrochemical industry, they want to sell this stuff, and the best way to sell it is to make it competitive financially against fossil fuels. So yes, there are many researchers very actively doing everything they can to bring these pricing down. But the fact is it's difficult. And you saw that graph. That's a lot. Many hundreds of man years have gone into getting that graph as good as it is, and it's got a long way to go. And as I said, pretty much every pathway is more complicated and thus more expensive than taking oil out of the ground and processing it and turning it into jet fuel, unfortunately.
William, can we grab the questions back, or have you lost that there?
Can I just ask you about I think there's a small airline in Canada which operates exclusively electric planes for short, and I think it's a.
Okay, you're thinking of Harbour Air. They're operating a de Havilland Beaver. Right, this is not yet operating commercially. They have developed this aircraft, they have flown it. It is a bit of a one-trick pony. It will fly 20-minute tourist flights with about 3 people plus the pilot. If you look at, take a look at pictures of their aircraft online and just look how low it sits in the water, and you get an idea of just the sheer weight of batteries in that aircraft. Well, what they're doing is quite impressive. It is definitely a step in the right direction. Now, I've flown electric aircraft. They are test flying electric aircraft. I do not think battery electric aircraft are the future. I think it is a necessary part of the trajectory because of the problems we are solving on aircraft like the E-Cub and the Harbour Air Beaver are the problems you need to solve in order to then run commercial hydrogen fuel cell airplanes, because the fuel cell just replaces the battery, but all the other problems are the same. So what is going on there is not an end point, but it, I think, is a necessary point in the trajectory towards where we need to be. Change to the back.
What do you think of the solar powered version of the hybrid vehicles?
So what do I think of the solar hybrid Airlander? I like Airlander. I think what they're doing is very clever. I think they have designed out a lot of the fundamental problems that have afflicted airships as a commercial prospect in the past. However, I also think that what they are doing is going to be a niche product. I really hope they sell aircraft. I believe they have the ability. I think the aircraft is, I'd ideally love to go in it, but I think it will find niche applications for things like ecotourism and high value travel. They're not going to solve mass transport problems with it. And yeah, put solar panels on it. Why not? You've got huge amounts of area. Let's do that. Make it more efficient. Great. I know a lot of the team at Hybrid, and I think they're really clever people who are doing stuff right. I just don't think it's going to be mainstream. But airships have not been mainstream since 1930.
Okay, you're looking at some of the questions from home.
Go for it.
Can we make planes run on solar energy?
Can we make aircraft run on solar energy? Yes. We take our solar energy, we turn it, if we're a small training aeroplane, say, we use it for charging up our batteries. We've actually got enough solar capacity at the factory at Little Snoring where we built the Sherwood Eco. We can do this. And one of these days we probably will, just to prove a point. Can we turn solar energy directly into hydrogen? Yes, there's technology to do that. Are we going to put solar panels on an aircraft and run it only in very narrow niche applications? The Airbus Zephyr aircraft, for example, which are unmanned high altitude aircraft that have phenomenal endurance records and done some really clever work in intelligence gathering, that does that. Passenger aircraft, no.
Until aviation reaches net zero, do you see any potential for inexpensive technology that has been proven to algorithmically reduce aircraft fuel burn and hence emissions by 1 to 2%?
Do I see short-term gains for bits of short-term cleverness? In essence, we're doing that already. All of the airlines, all of the manufacturers are constantly looking for all the small gains that give them commercial advantage. Conveniently, the less fuel you burn not just makes your emissions less, it makes the airline more profitable. So everybody's trying to do that.
Okay. On the energy balance diagram, the numbers emitted by the Earth don't quite add up. Why?
I can only suggest, I did show on my slide the paper I nicked the diagram from. Go and read the paper.
Okay, fleet replacement. What proportion of the UK's fleet is replaced each year? And what about the global fleet?
I'm taking numbers off the top of my head here, so I may be a little bit out, but I think the annual replenishment rate of the airline fleet is around about 4%, which is an issue actually, because we may need to replace these aircraft with much more efficient new technology aircraft faster than the average 25-year replenishment rate. And I'm sure there's plenty of airline financial directors who have scratched their head over that question as well.
Okay, Stuart has asked a question about contrails, and I think we've answered those. Simon Calder the other day said, switching to sustainable aviation fuel could see airline prices increase. What are your thoughts on the long-term viability?
I think every solution we're looking at here at the moment is going to be more expensive than what we're doing right now. Therefore, it is highly likely that airline ticket prices are only going to go up unless somebody manages some amazing breakthrough in order of magnitude cheaper production of efuels or hydrogen and the aircraft to go with it. But in the short to medium term, I'm afraid I do believe that ticket prices are going to go up. But honestly, they would anyway, because fossil fuel prices are going up too.
Okay. There is a cost in producing SAF. The process has some kind of footprint. What is it?
So the cost and footprint of producing SAF. So there was a slide I showed that showed the wide range of different pricing. And as I say, if you go to the report, you can see all of that in a lot more detail. The different SAF standards vary, but the best SAF standards typically have about 40% of the carbon footprint of using fossil fuels.
Is there any other SAF where there is no carbon base?
Are there any sustainable fuels where there is no carbon base? Well, hydrogen or ammonia have no carbon base. Now, clearly, the current production methods tend to use carbon fuels to create it, but that is not necessarily the case. We can do it with nuclear power, we can do it with wind energy, and so on. But if we're going to use those no carbon fuels, we need aircraft designed to operate on them.
Contrails are small when you look up at the sky compared to the enormity of the sky. Can you explain further?
Yes, certainly. So the contrails are small and they are short-lived, but their impact is so much greater whilst they exist than the CO2. CO2 has tiny effects, but over a very long period of time, and of course over the whole planet. So it's a course of magnitude.
In Chris Goodall's book, What We Need to Do Now for a zero carbon future, he says that the UK needs 20 times increase in renewable energy. It sounds like he may be correct, ?
So this is about, I don't know the book, but somebody called Chris Goodall, called What Do We Have to Do Now? Projecting we need about a 20-fold increase in renewable energy in the UK. And the questioner suggests that's probably correct. I think that's probably correct too.
Why didn't the report consider planes that are considerably or partly battery powered? They are surely part of the overall solution.
Right, that's a very good technical question. So the question is, why did the report not consider battery electric aeroplanes? Well, I am a test pilot. I've flown battery electric aircraft. In fact, the only entirely British designed and built all electric aeroplane is the one I'm currently test flying. We have currently achieved, with a payload of me, we have reached a ceiling of 6,300 feet, and we have managed an endurance of 54 minutes plus safety reserves that would certainly not be enough to meet airline safety standards. That is not going to solve the passenger transport problem. Our next 2-seat training aeroplanes that will give you an hour's endurance for training are certainly achievable. Pipistrel in Slovenia built one that will give you about 45-minute lesson. We are shortly to fly one that will give you an hour. So it will replace a small part of the estate, but batteries are simply much too heavy on any current or projected technology to be viable for mainstream passenger transport, and therefore the report made an early decision not to consider them.
As a pilot, if I had a rear view camera, how would I control my contrails?
If you had your rear view camera as a pilot, you would be looking out the back, and assuming your it's in the daytime, so you can actually see them because it's a bit difficult at night. You would aim to change your trajectory or your altitude until the contrails stop. But as I said earlier, that's all very well if you're a spy plane at 60,000 feet over Russia. It's a bit difficult to do in controlled airspace when you've got aircraft above, below and to either side of you who do not wish to have your close company.
Trying to rephrase this, and I don't think I will. Are e-fuels produced from small modular nuclear reactors really a solution? Does the technology exist?
Are e-fuels from small modular nuclear reactors a solution? Does the technology exist? They may be a solution. Rolls-Royce certainly would like to sell us that solution. I think they may well be right. At the moment, we simply haven't done it to prove it's possible, but on paper it is.
Is it not a good idea to have a little nuclear power station by Heathrow Airport, plus cutting out massive amount of moving electricity around the country, and then build our own, split our own hydrogen, whatever it is? Is that not a
so the question here is, could we reasonably put a small nuclear power station next to Heathrow, presumably pipe in the water? Thames Water, incidentally, are the biggest leakers of all of the water companies in the UK. So I'm sure they would appreciate Heathrow's investment to help them solve that problem. And electrolyse the water on site to create the hydrogen. We've all had that discussion. It does look like quite a good idea, but the amount of R&D to get to that point will be very far from trivial. But on face of it, it seems like a potential quite good solution in the long term, yes.
I'd have a problem with the residents.
Yeah.
Are you saying your residents are fine at the
It wouldn't be a problem to me, no, but they don't like change.
No, I think there is a fundamental problem that probably nobody wants a nuclear power station built next door. But equally, lots of people aren't deeply impressed at having an airport built next door. So, but this is fundamentally a human and political problem. That's not the technological problem.
So there we have this large, heavy missile full of people going by that dives into this small nuclear power plant just outside Heathrow. Heathrow is no longer a problem.
Seriously, the only person I have ever met who thought that aviation safety standards were unreasonably low was somebody who'd come into aviation from the nuclear industry. They are a very, very safe industry. They're very good at getting this stuff right. So I'm fine living next to a nuclear power station, apart from they're rather ugly. I can think of many things I would rather not have next door.
I worry more now than I did as a result of the terrorism that's going on in the world. LTAG work for ICAO shows SAF as the main fuel for all scenarios up to 2050 and for some time beyond. New fuels, including electric ones, not only need new aircraft, but also need new distribution systems worldwide to allow these options to be viable. SAFs are being used now and need essentially no change. Not sure where the question is there.
I think
SAFs are dropping.
I think that's the point in the conference where somebody says, I don't so much have a question as a point. Their point is sound, except for the fundamental problem that there isn't the feedstock to produce enough biofuel.
Another one with easy one to answer. Why did you study ammonia as an alternative solution when no potential fuel producers are working on that solution to date?
The world has a massive production and distribution system for ammonia. It's just used in agriculture at the moment. there, and on paper it is potentially usable. People are building research ships to run on it. In theory, it could be run on an aircraft. Therefore, it appears important that we research ammonia fuel aircraft, even if we have to do all that research and conclude actually it was a bad idea. But it would be irresponsible to discount it without doing that research.
Is it possible that the 5% estimated increase in air travel every year could be reduced?
Is it possible to reduce the 5% general trajectory? This is not predicted. This is what we've been doing for decades, increase in air travel. The problem is most of that growth is in the new middle classes of countries like India, China, Brazil, who are steadily approaching the level of personal wealth that we are used to here. It would take a very brave politician to go to those countries and say, no, you can't have the wealth and the travel privileges that we are used to in Europe and America. And I'm pretty certain if that politician did say that, I could guess what the Indian and Chinese and Brazilian politicians would say back.
The infrastructure and equipment that the oil industry uses to create and distribute fuel is vast and has obviously been developed over decades. Would the infrastructure and equipment needed to create and distribute hydrogen need to be of a similar scale, and how much do we know about it and its cost?
Okay, so the question is, would hydrogen distribution infrastructure have to be on a similar scale to that of fossil fuel distribution and storage? Yes, it would have to be. It would be very, very expensive. It would be very disruptive, but I think it needs to be done.
If the airlines should be upgrading their fleet in a shorter time span, do you believe the airline industry will shift to leasing aircraft from the manufacturers?
That question is about airline economics, which I am completely unqualified to answer, so I'm not going to try.
How viable are pure electric aircraft that emit no greenhouse gases and are powered by batteries?
I think I've answered the question already. Pure battery electric aircraft are viable as training and sports aircraft. They're not viable as transport aircraft.
Are they even that?
Yes.
So, because you get 1 hour's flight, how long is it on the ground for to charge up?
The Pipistrel Velis Electro, which is currently the world's only certified electric aircraft that's usable for training, will give you roughly a 2-to-1 ratio of charging time to flying time. That will work in a flying school environment, albeit it's more expensive than fossil fuels. Everything is unfortunately more expensive than fossil fuels.
I wouldn't be very happy with my training aircraft being on the ground for twice as long as.
Well, at the moment,
yeah.
Most training aircraft are probably running on around 1-to-1. And that is where we are right now, not necessarily where we will be with the new generation lithium sulfur batteries, for example. So what we've got is just acceptable. What we will get, I think, will be better, but I don't think it will be viable for transport, but I think it will be viable for training and sports.
The solutions for motorbikes that often you pull out the battery and slot the new one in.
So the question here was, can we go for swappable batteries? We've looked at this, and my take on it right now is the batteries that you were flying in the E-Cub I'm flying, in the Velis Electro, similar aircraft, are probably 2/3 plus of the total value of the aeroplane. They're also very fragile. You drop it, you have just wiped off a huge amount of value and potentially caused a rather problematic concentrated fire. The military, I don't think will struggle with that, because that doesn't look much different to loading and unloading bombs. I think your average civilian flying school would struggle massively to provide that level of control over putting battery packs on and off. So I think in some environments that is a solution to the problem, but in others it's just not going to work.
We had Phil O'Dell here, the Rolls-Royce test pilot. He talked about this a lot.
Pod, yeah.
And he said that for ever to be commercially successful, you would need to have the infrastructure at all the airports that your airline flew to put batteries in within the sort of hour turnaround times that they would expect.
We could discuss this
from that.
We could discuss this for cars, couldn't we?
Yeah.
Cars could theoretically have swappable batteries, but they don't.
Yeah.
There was an attempt to do that. It never succeeded.
Well, and actually the Pipistrel Alpha Electro, the predecessor of the Velis, did that, but Pipistrel found it didn't work and they abandoned it and went for fixed in batteries for the Velis. So it's a lovely idea until it's presented with reality.
I guess looking at other webinars we've listened to here and elsewhere, a lot of the batteries in these aircraft, or the projected aircraft, the battery is part of the monocoque of the aeroplane. Is actually the structure, and it makes it very, very difficult to swap them over. I mean, that Phil's aeroplane as an example. That's that kind of aeroplane.
And it substantially is in the Velis as well. It's not in the Cub, and it won't be in the Sky Ranger. But when you are chasing the maximum possible payload, and you have a really, really heavy energy source, then integrating the energy source into the structure is an obvious thing to do. This is what Tesla do, of course, with their cars, but it comes with downsides.
Sure. One final question.
Yep, there's two left. Hybrid electric planes can use a similar battery power to the plane. Sorry, hybrid electric planes can use a smaller battery to power the plane, with the battery continuously charged by a turbine that runs on kerosenes or efuels. Or I guess you could have a ram air turbine, couldn't you?
Okay, this is a fun question, and one that often finds itself into other lectures I give. So the question is about hybridization. Now, there's a company in France called Voltero who have converted to hybrid IC electric a Cessna 337. And it's quite viable. They've flown over 100 flights. They've actually flown it from Paris to see us at Cranfield. And they reckon that compared to a conventional powertrain on the same airframe, they are saving about 17% on fuel burn. The configuration of that is somewhat similar to, say, a Prius. It's basically using a combination of battery electric and IC to optimize both and make something more efficient. And 17% is well worth having, but it's not zero emissions. A thought experiment I've played with is for a lot of the shorter routes, and the one that appears on most of my lecture slides is Jersey-Guernsey. Jersey to Guernsey, airport to airport, 24 nautical miles. Typical small commuter aeroplane can do that in about 15 minutes. But public transport safety rules require, when you look at where your available alternates are and so on and so forth, round about an hour and a quarter of reserve fuel. So why don't we carry our 15 minutes of mission fuel in batteries, and we'll carry an hour and a quarter of fuel in kerosene with an APU that back charges the batteries, and we only ever turn on if we're diverting. That actually looks like quite a sensible solution for some routes, and there are aircraft that may do that. That certainly is the route that Voltero are pursuing, and no great secret, Cranfield are working with them on that, and I think they've got some really good ideas. So yes, that may be a solution for particularly shorter routes that are public transport and nonetheless require a lot of safety reserves, such as between islands.
Okay, and the last one I've got here. Is ammonia asphyxiation in a crash really a likely problem? How about the volatility of ammonia? Wouldn't it all evaporate anyway?
So the question is, Will ammonia evaporate before it asphyxiates the poor people on board the aircraft after you have crashed your ammonia airliner? This is precisely why I'm advocating we need to do a lot of research, because honestly, I think anybody who thinks they can answer that question is guessing at the moment. And I don't like guessing, so I'm just going to say we need more research. Please pay me to do it at Cranfield, but somebody needs to do that research, even if it's not us.
You have exhausted the questions from home. I apologise those at home where I've paraphrased your questions slightly differently, and I apologise for those we've missed because the questions have already been answered. But I have no more questions here. Any more in the room? Shall we move on?
Wonderful. And just to remind everybody, on my last slide there at the bottom, that is the link to read the Royal Society full report.
On behalf of the committee members of the Heathrow branch, the members that are here tonight as well, I've got to thank you for giving up your valuable time to talk to us. I know it went on longer than we discussed, but
It means people were interested.
People were interested. So I'm going to say thank you very much indeed.
Thank you.
Thank you to your family for sparing you tonight. From us,
Very kind indeed.
Please accept that. Thank you all for coming. I guess thanks all of you for coming. Come again. We'll keep finding the nice things to look at. If you're watching at home, if it all went wrong for you, if the noise and the feedback went wrong for you, let William know. Use the links you've got. So let us know. Give us your feedback on how it worked. Thank you for coming at home. 200 of you. Was it that high by the end?